In Chapter 3, Section 6, we're looking at functions. Our objectives are to identify relations, domains, and ranges, identify functions, use the vertical line test, and use function notation. Find the domain and range of each relation. Let's review. Domains correspond to all of the input values, which are the x values of the coordinates, where the range corresponds to all of the output values, which are the y values. A way to remember the domain and range with the x and the y is to remember domain, input, x values, range, output, y values. D comes before R in the alphabet and X comes before Y. Domain, input, X values, DIX, range, output, Y values, ROY. For the first set of ordered pairs, we see that the domain, I can abbreviate that with D, is a set of all just the X values. So we can write it as 2, 0, -1, and -2. However, it is common to write these in order from left to right on the number line, -2, 1, 0, and 2. Our range is the output or the y values. The range will include in this example 3, 0, -5, and 6. Those are all of the y values. In order from left to right on the number line, we can write them as -5, 0, 3, and 6. For part B, our domain consists of all those x values, 3, 3, 3, and 3. Since they're all, the x values are 3, we don't really need to list them separately. We can say that the domain is 3. And I'm using those squiggly brackets. The range are all of the y values, and that will include 1, -2, 0, and 6. We're using set notation, which is squiggly brackets, going from left to right or low to high on the number line, -2, 0, 1, and 6. A function is a set of ordered pairs in which each x coordinate has exactly one y coordinate. That means if you're looking at a list of points that is in a relation, there should be no repeated x values with different y values. So let's determine if the first relation is a function. Notice all of the x values that we have: 10, 5, -3, -2, 2, -1, and 6, 5. There are no repeated x values, so we can say that this relation is a function. In the second example, we see that we have the x values of 3, -3, -3, and 2. We have repeated x values here in the second and the third points, and the y values are different. So this would not be considered a function because each x coordinate has more than one y coordinate. So this is not a function. Graphs can be used to determine if a relation is a function. We can use the vertical line test. If a vertical line can be drawn so that it intersects a graph more than once, the graph is not the graph of a function. If no such vertical line can be drawn, the graph is that of a function. For the first one, we can see the graph of a circle. If we draw a vertical line, we see that the vertical line drawn as shown goes through the graph or intersects the graph more than once. So we can say that this is not a function. It does not pass the vertical line test. Let's look at the second example. If we draw a vertical line, we see here that it crosses only once. And no matter where we draw that vertical line, we would see that each vertical line would only intersect the graph at exactly one point. Therefore, this passes the vertical line test. This is a function. And for the last example here, it's the graph of a parabola that opens up. We can use the vertical line test to determine if the graph is a function. Notice that every vertical line that we draw will only cross at most one point. So that means this graph is also a function. We can also evaluate functions. For each function, find the value of f of -3, f of 2, and f of 0. F of -3 can be found by replacing the x is our input, that's part of our domain, replacing the x with -3 and simplifying the result. So here we get f of -3 is -1/3 times -3 minus 5. By simplifying this, -1/3 times -3 is a positive 1, and 1 minus 5 is -4. So we can say that f of -3 is equal to -4. When -3 is the input, the output is -4. Let's find f of 2. F of 2 is found by replacing the x in the original function with 2, and then simplifying the result. -1/3 times 2 is -2/3, and 2/3 minus 5. When we simplify that, we get -2/3 minus 5 with a common denominator of 3 is 15/3. So we get -17/3. That is f of 2. Then finally our f of 0. When we plug 0 into the original function instead of x, we get 1/3 of 0 minus 5. When we simplify this, we get f of 0 is equal to -5. In part B, we're looking at a quadratic function. It's a function raised to the second power. You see x to the second power. So let's evaluate f of -3 here. When I evaluate functions, I do like to typically put the value that I'm substituting in parentheses, so I'm very careful about the order of operations. So again, I took my original function and replaced the x with -3. Now remember the order of operations, you want to do exponents before you multiply or divide. So when we take -3 raised to the second power, that's going to be 9. This -2 times -3 and -2. Our next step in the order of operations is to multiply. 9 times 3 is 27. This -2 times a -3 gives us a positive 6 minus 2. Now we can do 27 plus 6, which is 33, minus 2 equals 31. So f of -3 is equal to 31. Now let's find f of 2. By substituting in, replacing every x with 2, and then using the order of operations to simplify, we can evaluate the function. So we do the powers first. So 2 squared is 4. This is going to be 3 times 4 minus 2 times 2 minus 2. Order of operations, we multiply first. So it's going to be 12 minus 4 minus 2. And then we take 12 minus 4, which is 8. 8 minus 2 is equal to 6. So f of 2 is equal to 6. Then we can evaluate f of 0, replacing each x in the original function with 0, and simplifying the result, we get f of 0 is equal to -2. Let's evaluate the absolute value function, the absolute value of -3 minus x. Let's replace any x in the function with -3 when we're evaluating f of -3. It's the absolute value of -3 minus a -3. Remember that the order of operations, so we have a minus, a negative becomes a plus. We want to do what's inside the absolute value first. So negative 3 plus 3 is going to be 0, which simplifies to 0. So f of negative 3 is equal to 0. Now let's find f of 2. F of 2 would equal negative 3 minus 2. Let's evaluate what's inside the brackets first. Negative 3 minus 2 is negative 5. And then when you take the absolute value of negative 5, you get 5. So f of 2 is equal to 5. Let's find f of 0. We're replacing the x in the original function with 0, and then simplifying the results. So f of 0 is equal to 3. If f of 4 is equal to 8, write a corresponding ordered pair. We know that f of x, where x is the input, when evaluated, is solved for y. So f of x is equal to y. In this case, the x, our input, is 4 when our output is 8. So we can write this as an ordered pair, 4, 8.